We're going to talk about measuring data, and we're going to be measuring data for center, spread, and for relative position. Let's start with measures of center. A measure of center describes a typical data value. These measures of center are also called averages, and again describe that typical data value, which we can do through a mean. This is what we typically think of as average, but the true terminology is mean, and that's the sum of all the data values divided by the number of data values. The median is the middlemost number. If there isn't an exact number in the middle, we'll average the middle two. The mode is the most frequent data value, and there could be a couple of modes. We might have some data values that both show up frequently. The mean is described in a couple of different ways. It's the same formula, but if we're using mean to describe a population's average, then we would use the symbol mu, which is a Greek symbol for m. If we were using it to describe a sample, we would use lowercase m. And x bar is another way that we can describe the mean, which is just generic, either the mean for the sample or for the population. You'll notice that I've got it described here using sigma notation. This is a capital sigma right next to the x in the fraction. And that means the sum of all of the x's or data values divided by n. So mu, the Greek letter, describes the population. So we'd say that is a parameter. And M, the regular Arabic letter, is for a sample, which we would call a statistic. Okay, here's an example. Diaper changes per day. So let's say that we've got 6 babies and we tracked how many diaper changes were done in the span of a day. So we've got these data values, 3, 4, 4, 5, 6, and 8. We want to find the mean, median, and mode. To find that mean, we're going to use mu, thinking of this group as a population. We just add up all of the data values and divide by 6, which is the total number we have, and we've got a mean number of changes per day of 5. The median we're going to find from the middle of the data. The data's got to be in order, and our data is. So the median would actually live smack in the middle of the data, which would be between 4 and 5. Since there's not an exact middle, we're going to average those two middle numbers. 4 plus 5 divided by 2, the halfway point would be 4.5. And then finally, the mode. The mode describes the most frequent data value. In this case, there's a single mode, and it's 4, which shows up the most often at 2 times. So our mode would be 4. How do we choose the best measure? So we want to go back to thinking of these measures of center as describing a typical data value. Here's an example. We want to know which of these measures is the most representative of home prices in Springfield. So someone has told us that the mean home price is $679,000, the median home price is $232,000, and the mode for the home prices is $124,000. So if we are moving to Springfield, shopping for a house, how much could we expect to pay? Would it be the $679, the $232, or the $124? Let's take a look at the data. Here's the data that was used to compute each of these measures, and you'll see that there was a $3.5 million home sold, very much not representative of a typical home price. And that brought the mean up. So when we added all of those values together, we ended up with a higher mean than would be typical of these home prices. $124,000 is actually the lowest home price in this data list. So it's also not representative, but the median, the one right smack in the middle there at $232, would be, for home prices, the most representative measure of center. We can also talk about measures of spread. Measures of spread describe the variability or how spread out our data values are. The first measure of spread is the range. It's the maximum minus the minimum, highest value minus the lowest. The mid-range gives us the middle of the data, halfway between the minimum and maximum. So we average those two. Min plus max divided by 2 is our mid-range. The standard deviation, we're going to look at the formulas here in just a second, but this describes how far a typical value is from the mean. Okay, here's our standard deviation formulas. There are 2 of them. The good news is that I'm going to show you how to use technology to come up with these measures, but you also need to know exactly how you're using these measures in terms of describing it either for a sample, approximating a larger group, or as a population. So let's back up. The deviation, first of all. The deviation is just how far any data value is from the mean. So that would be the x, the data value, minus the mean. So when we put the word standard in front of it, which also means average or typical, we're looking for that standard distance from the mean, or the average, typical distance from the mean. You'll notice in both of these formulas, we're taking x, the data value, minus the mean. So we're adding up all of these differences and dividing them by the number of data values. The difference is, though, is that we square them before we add them up, and then we take a square root in the end. And that's just so we don't have negatives and positives canceling each other out. 2 other things that you'll notice is the n-1 in the sample standard deviation versus the n, which is what we expected in an average, dividing by the number of data values. If we're doing a sample standard deviation, we're using a smaller set than we really want to be describing. So the sample standard deviation has this unbiased estimator in it of n-1. If I divide all my differences by a smaller number, I'm going to end up with a slightly bigger standard deviation. I just want to bump that out so I can use it to approximate the standard deviation for a larger group. Most typically, we use a sample standard deviation, but once in a while, we do have all of our data, and we can describe the distance from the mean using the population standard deviation. Okay, so again, sample is described with S, just the regular Arabic letter, and the population standard deviation, that parameter, is described by a Greek letter, lowercase s, which is sigma in Greek. The variance shows up once in a while. It's the standard deviation squared, or you can think of that without the square root symbol. We're going to let technology do those calculations for us. Okay, so I use technology to do these calculations. So here we've got a data list, a distribution, heights of dogs in centimeters, and they span from 32 to 74 centimeters in height. So our range is 74 minus 32, which is 42. Our mid-range is going to be smack dab in the middle of that range. It's different than the median, though. It's not a data value. It's right smack in the middle of the range. So 32 plus 74 divided by 2 puts me at 53. So range and mid-range. One quick note on the mid-range. It's showing up here in the measures of variability, but it is also very much a measure of center. So a little bit of gray area there on the mid-range. I also have the standard deviations. So for these standard deviations, this is where I use technology. The population standard deviation turned out to be 13.87, so about 13.9 is the distance of a typical dog's height from the mean. And for the sample standard deviation, notice how that's a little bit bigger. That's because this number can be used to approximate a standard deviation for a bigger group. So 14.989 is what we get for that sample. Again, we typically use the sample standard deviation because we're using it for inferential statistics. We're using it to draw a conclusion about a bigger data set. Okay, so technology. I do have videos that show you how to use Google Sheets, Desmos, and the TI-84. There are lots and lots of statistical programs out there. But these are some that are readily available to everyone. So you'll notice that we can come up with a mean using either the average or mean command in Google Sheets or Desmos. The median is the median. The standard deviation for the sample is just STDEV. It's the population that has a P on the end of it. For the TI-84, we can run a single command, one variable statistics, that will bring up all of these measures for us. Let's move on to measures of relative position. These measures are for specific data values compared to others in our set. So measures of position. So we're looking at individual values now relative to others. The z-score. The z-score tells me how many standard deviations a single value is from the mean. A quartile divides up my data into fourths. So if I'm referring to a specific quartile, I'm looking at a group that's been divided into 25%, 50%, 75%, or even 100%. So quartile 1, 25% of the data is below that value. For quartile 2, this is the median, half of the data is below that value. Quartile 3, 75% of the data is below that value. Percentiles are similar, but instead of breaking the data up into groups of 25, we break them up into single percentages. So we'll look at some percentiles as well. So for example, 60th percentile is the value that has 60% of the data below. A lot of standardized tests like the SAT, I don't know if the ACT is done this way. If you have a baby and you take them in and you get them measured and weighed, they give you the percentile. Because the question really isn't, what is my score, but how does my score compare to everybody else that took this test? Let's go ahead and start with the z-score. So the z-score tells me how many standard deviations away I am from the mean. Most values are about 1. The z-score takes the data value minus the mean divided by, I'm doing the sample standard deviation. You could also use a population standard deviation here. I already calculated the mean and the sample standard deviation for these dog heights. So I'm going to use 55 and 14.989 to find these z-scores. So the first example, for a height of 51, it's below the mean, so I'm expecting a negative z-score. So 51 minus 55 divided by that standard deviation gives me a negative 0.267. So I'm about a fourth of a standard deviation below the mean. The z-score for 74, this is at the top of my data list. So I'm expecting a positive z-score. It's above my mean. So I find the difference, 74 minus 55, and divide it by a standard deviation. I'm more than 1 standard deviation away. So I'm 1.26, about 1.25 standard deviations away from the mean. Next, we're going to do the z-score for a mean. If we had 55 in our data set, we could find its z-score. The z-score is 55 minus 55. Well, whenever you've got the mean, its z-score will always be 0 because we're looking at the distance compared to a standard deviation from the mean. So 55 minus 55 gives me a z-score of 0. Next are the quartiles and the 5-number summary. Again, we've got our heights of dogs in centimeters. Here comes our 5-number summary. You can think of this as breaking up the data into 25% chunks. So I start that with my minimum of 32. Quartile 1 of 40 is at the quarter of the way through point. Quartile 2 is my median. That's the halfway through point. Quartile 3 divides the lower 75% from the upper 25, and then finally my maximum. So if I go up to my data set and take a look at where these are, I'm just going to put each of those arrows up there. Notice that 58 is my median. It's right in the middle. 40 is the median of the lower group, 32, 40, and 51. 40 is right smack in the middle. 67 is the median of the upper group. So we can think of those quartiles as medians of the lower half and medians of the upper half as well. We can also compute these using technology. It is important that your data is listed in order smallest to largest as you're finding these. We can describe quartiles and all the values actually in this 5-number summary using a box plot. So we'll be working on these in class. Notice that the box is between quartile 1 and quartile 3. This contains the middle 50% of values. Those whiskers give me the lower 25% and the upper 25%. There's a little bit of variability in how these box plots are displayed. Some show any outliers as dots at the end of the whiskers. So you'll see a little bit of variability there. Okay, so we're going to look for outliers in this group, and we're going to start with that inner quartile range. That was the box that we had in the middle 50%. So the inner quartile range is quartile 3. So that would be our purple arrow minus quartile 1, which is our blue arrow. The outliers are computed using this number, and we're going to find them because they're going to be either below quartile 1 minus 1.5 times the inner quartile range. So that's going to push things out to the lower end, or you're going to be an outlier if you're above quartile 3. So you're outside of that box by 1.5 times the inner quartile range. So we've got formulas to see how far outside of that box you would need to be an outlier. Let's compute these for our distribution of heights. Okay, this is my inner quartile range. So the box that I've got in yellow around my data is my inner quartile range. That's my middle 50%. So for my inner quartile range, that's going to be 27, 67 minus 40. I know that the outliers are going to be the data values that are 1.5 times the inner quartile range away from the box. Okay, so that is below 40, so quartile 1 minus 1.5 times the IQR. So that gives me below negative 0.5. I don't have any heights that are below negative 0.5. Or they're going to be above 67, so that's the edge of my box, plus 1.5 times 27. That gives me 107.5. And again, I don't have any heights that are beyond 107.5. So this data set has no outliers. Let's take a look at percentiles. This is another measure of position that gives us some really good information about how we compare to the bigger group. So again, we've got our heights of dogs here. We want to find the percentile rank of a score. This gives me the percentage of scores that are below my score. Score is another word for a data value. There is some variability in these formulas. We're going to use this formula here. That's the number of scores below times 100 divided by n. Then we're going to round it to get a nice whole number. You will see some that add 0.5. You'll see some that add 0.5 times the number of scores equal. Just know that statistics is not an exact science, but instead there's many ways to sort of get at the same analysis. Okay, so always round to the nearest whole number. Let's take a look at an example. Turns out that 51 is in the 29th percentile. Let's see where that comes from. So I've circled 51 up here in yellow. There are 2 scores below. So I'm going to go 2 times 100 divided by 7. Or you could do 2 divided by 7 first. The number of scores divided by the total. So 2 below divided by 7 times 100. Then I want to round this to get a nice whole number. So we call that the 29th percentile. We also want to be able to find the score, the data value at a given percentile. We're going to do this by finding the location. So we're going to find the location by taking the percentile and multiplying it by the number of data values. Technically, we take the percentile, which was a whole number, and divide it by 100. That just gives me the decimal form times n. We're always going to round up to the next whole number. This is really important. Otherwise, if you round down, you're going to end up picking a value that does not have a big enough percentage below it. Okay, here's an example. We want to find the location of the 60th percentile. To calculate this, I want to do the 60th percentile, 0.6 times 7, or 60 divided by 100 times 7. We get 4.2. But I'm going to round up because the 4.2 spot is not high enough. The 4th spot certainly isn't high enough. So I need to go to the 5th data value. Okay, so the arrow that I've got there in yellow is between positions 4 and 5. So 58 is the fourth data value, 63 is the fifth data value, 4.2 is in between there. So 58 is going to be too small, so I need to go up to the next one. So that means that our location of the 60th percentile as a data value is 63. So you're ready to learn more. Take a look at my videos. I show you some different ways to work with these measures using technology and lots of examples both by hand and using that technology.